So next we move on to unit 3, sequential logic circuits and clocking strategies. So the in this unit we have the main topics as non-stable sequential circuits, so non-bistable sequential circuits, and timing classifications also important topics as there. It was an important topic, and self-time circuit design. So you have the timing parameters within the circuit itself, so it is generating the timing signals within the own circuit. So that is self-time circuit design and synchronous design. So very few topics in this unit, and pipelines and all, static latches and dynamic latches and registers. So these are the important these are the total topics available, and among these you may expect questions from non-bistable sequential circuits and static and dynamic latches. Okay, straightly we move on to unit 3. So this is sequential in the sense it must have the next state is depending upon the current state and the previous inputs. That means it must have the copy of the earlier states. That means it must have the memory. So if the circuit is sequential, means it should have the memory as well as the feedback path in the sense there is a path from the output to the input back to the input, so that we call that to be a feedback path. On static latches, so before going to the topic, let me introduce what is latches and flip-flops. Latches are level sensitive. This is the signal level. See, these flat regions we call that to be a levels, and these high regions and fall regions like this, these are the edges. So rising, this is the rising edge, this is the falling edge. So if the device is operating under at the edges, means we call that to be a flip-flops. If the devices are sensitive to the levels, means then we call to be a latches. So latches is a uh, level sensitive circuit. Here you can see level sensitive circuit. Okay. So if there are two modes, latch is set to be in transparent mode when the clock signal is high. That means whatever the signal is available at the D input, it will be copied to the Q output. That is the transparent mode. When the clock is low, the input data is sampled on the falling edge of the clock and it is held stable for the entire phase. This is in the hold mode. So earlier we have seen the pre-charge mode and the evaluation mode. The same here it is transparent transparent mode. The pre-charge mode is here for the hold mode, and the evaluation mode is your transparent mode. So the input must be stable before the, that's why. So for a single flip-flop is a single storage memory element. Okay, it can store only one bit of information. A register is a collection of flip-flops where it can store different more amount of informations, more bits of informations, depending upon the number of flip-flops used. If you are using three flip-flop, means it can store 3 bits at a time. So these 3 bits can be used to represent 2 power n, that is 2 power 3, as 8 levels. So these three inputs, with these 3 bits and these three flip-flops, we can store at least 8 levels. And if we are using 4 flip-flops, means then we can store 4 bits that is used to represent 16 different types of values. So 2 power 4 is 16, so we can have 16 different possible values for that. Okay. So, and dynamic latches and registers, when the, so again the same dynamic with the presence of the clock. So it will be in the transparent mode and the hold mode. So for higher clock, the latch will be in the transparent. So dynamic edge trigger and advantages, what are the, and C squared mass logic, that is clocked CMOS registers, clocked complementary mass transistors. That's why it is C squared mass transistors. See, clocked CMOS logics, and true single phase clock register. So So if in your clock there is on and off signal, so true single phase means either clock high or clock zero will be used. Not both the signals, clock and clock bar, will not be used. That is true single phase clock registers. And pulse register, only a short pulse. So why we are choosing these types of because there may be a possibility of uh, there may be a possibility of overlap. So this is your clock signal, this is your CLK signal. CLK bar signal will be the inversion of this. So if it is high, so it will be low and it will be high. So this will be the clock bar signal. If these two signals, are, and so this has to be opposite to that of this. It has to start at the same time. It has to end at the same time. The same replication but inverted. So this is the situation for the two phase signals. If there is a delay in it, if there is a delay, then there may be a possibility of getting delay here. Okay, so there may be a uh, so here in these regions both are low. Okay, actually it should be complement of this, but this has been delayed and it has start with the start time, correct time. So there is a delay here, or if ulta, you can have a advance here and delay here. So in this way there might be a possibility of overlap. So if we are using both clock and clock bar, so this is the dual clock using. So we will be using a clock bar signal for the PMAS and clock signal for the NMAS, right, for the dynamic registers. So C squared mass register have the possibility of overlap of the signal, so that can be avoided with the help of true single phase clock register and these pulse registers. The pulse register, it is not, we are not using the clock signal in full form, just we are using the sharp pulse alone. So rising pulse and falling pulse alone, like this. At the end, as at the end or at the starting, we are having a simple pulse only alone. So you can notice here. So after that too, a little later, because if there is a delay means there may be a possibility of overlap also of this pulse also. So that's why it has been delayed. It has been little delayed, this pulse you can see there is a gap, little delayed it has been provided, and the pulse has been generated later. Similarly for the next clock, it has been delayed, data has been delayed little. So this is why it has been delayed, because if the signal gets delayed means there may be a possibility of this overlapping of the pulses itself. If it starts here itself means there may be a possibility of both the thing, if it is earlier delay. So that's why it has been delayed. So this is pulse registers. And register versus latch versus register pipelines. So pipelining operations parallel execution stage by stage, we call that to be and non-bistable circuits. We have three categories: Smith trigger, stable. Smith trigger is a device with two important properties. So there is a hysteresis property, we can say. While rising, the signal getting rise, it is moving in the one direction, it is moving in the one path. And for the returning signal, if we reduce it, it get returned in the another path. There is a gap between these two paths. This region is called as, we call this to be a hysteresis. This is possible only in the case of Smith trigger. That's why the symbol is also being represented like this. Okay. And monostable circuit, it will be having a single stable state, and a bistable circuit, a stable circuit, it will not be having any stable state at all. And timing classification, we have propagation delay and contamination delay. Contamination delay is the worst case delay, showing the maximum delay. Okay. mm, and these are the different types of and setup time, hold time. So setup time is the amount of time before the clock edge that must be stable before the rising clock arrives. That means the time elapsed, how much time it has been used by the data input to be stable before the clock edge is being getting arrived. So whole time is the amount of time after the clock edge arrive. After the arrival of the clock, how much time it has been, the data must be has been held stable for the flip flop to latch the value. So the flip flop has to transfer the value, right? So for how long it has to be stable, that time is the whole time. So these are the, and clock skew and jitter. Clock skew is the spatial variation, and the jitter is the temporal variations in the positive edges of the clock. And synchronous design, everything run in parallel, that is the synchronous design. And clock skew, again, the time difference between the arrival of the clocks, different arrival times of the clock, we call that to be a clock skew. And self time, I already told you, designing, and these circuits will have its own design parameters, and it will be using the signalings like request, acknowledge, and data. So if the center wants to send the data, means it has to send the request first. If the receiver device is free, then it will be transfer the acknowledgement. Then it will be transfer the data. So this is the sequence. So if a request has been sent, if the device is ready, acknowledge will be after the receiving the end of the at the end of the acknowledgement, data transfer will start state. So this is the uh, self-circuit design. So in at the back of this lesson, you can see only few tumors. You can have the all the tumors in this from this unit. Okay. So next we will move on with the unit 4 shortly.